Good afternoon, class. Here's elementary statistics practice test number 4, covering chapters 8 and 9. Chapter 8, hypothesis testing. Chapter 9, inferences from 2 samples. Again, here's the pledge. When we take the exam on our own. I can't emphasize this enough. However, we may use formula sheet, tables, and a graphing calculator. And here's chapter 8, hypothesis testing. A test of hypothesis is a formal statistical procedure used to make inferences or decisions about population parameters based on sample data. As I've mentioned before, everything is about the population using sample. It begins with the formulation of 2 competing hypotheses. Null hypothesis, also known as H sub 0, represents the default or status quo assumption, e.g. no effect or no difference. And normally we use an equality sign for that. Alternative hypothesis, H sub 1 or H sub A, depending upon the text, represents the claim or effect we are testing for. The process involves selecting a significance level alpha, which defines the threshold for rejecting the null hypothesis, commonly set at 0.05. A test statistic is then calculated from a sample data, which is compared to a critical value or used to compute a p-value. All of this will be discussed. There are 2 types of error in hypothesis testing. Type 1 error, rejecting H sub 0 or H0 when it's actually true, known as false positive, with a probability equal to alpha. Type 2 error, failing to reject H0 when H1 is true, known as false negative, denoted by beta. The power of a test, 1 minus beta, measures its ability to correctly detect a true effect. The conclusion of hypothesis test is either to reject H0 in favor of H1 if the evidence is strong enough, or to fail to reject H0 if the evidence is insufficient, never concluding that H0 is definitely true. That's the terminology that is being used. In a hypothesis testing, the rejection region and non-rejection region are critical concepts used to decide whether to reject a null hypothesis. Rejection region, also known as critical region, the set of values of the test statistic for which the null hypothesis is rejected. Non-rejection region, also known as acceptance region, the set of values for which we do not reject the null hypothesis. So we have a case like this one, or this one. This is a 2-tail test. For H1, we use the inequality sign. These 2 are 1-tail tests. This is more specifically a left-tail test. This is where the rejection takes place. And it's a left-tail test, as I mentioned. This is a right-tail test. The tail is in the right, and this is where the rejection takes place. So the sign not equal, left tail is less than, right tail is greater than. Okay. So the shaded region is the rejection region. Again, another way of writing it. I just wanted to make sure that everybody can see left tail, right tail, 2-tail. So in between is fine. This is do not reject H0. That means if we calculate the test statistic, these 2 values are considered the critical value, or the critical value, or the critical value here. So if it's in between, we do not reject H0, we fail to reject H0. If it falls in any of those tails, we will reject H0. Test type, as I mentioned, 2-tail. Rejection region would be here and here. Z is less than minus the alpha over 2 or Z larger than 0 alpha over 2. Otherwise, it's non-rejection. Right tail test. If you look at this one, for example, right tail test, when Z is larger than Z sub alpha, this is called Z sub alpha. This is called Z sub alpha, this point or the critical value. For left tail test, when it's less than that. For a two-tail test, we cut it in half and we put half of it on the right side, half of it on the left. When it's a two-tail test, that's so. If we put the two together, it gives us two normal distribution. In the case of a normal distribution, of course. This is where type 1 error occurs. This is where, and it's equal to alpha. This type 2 error happens, and this is the power of the test as far as the regions that are concerned. I'm going to answer the following. A test of hypothesis is always about the population parameter. Always. The observed value of a test statistic is the value that we calculated for a sample statistic. As the sample size gets larger, both type 1 and type 2 errors decrease or increase. They decrease. They become closer to the actual population. What is type 1 error? Let's define it. Rejecting a null hypothesis when it's true, false positive. Define type 2 error. Failing to reject a null hypothesis when it's false, also known as false negative. The value of alpha is called the probability of type 1 error. Beta is called the probability of type 2 error. As mentioned, 1 minus beta is the power of the test, correct decision, probability of rejecting a false hypothesis. So, preliminary conclusion, reject H0, fail to reject H0, true state of the nature. Null hypothesis is true here. Again, true state of the nature, null hypothesis is false here. So what happens when we are in this area? If we reject H0, so we know that it is supposed to be true and we make a mistake of rejecting it. That's called type 1 error. And because the complementary event failed to reject H0, they must add up to 1 is 1 minus alpha, which is correct decision. On the other hand, if the true state is that the null hypothesis is false, so the correct, and we make the correct decision, that's 1 minus beta. On the other hand, if we fail to reject it, okay, that's an error known as type 2 error, also false negative, failed to reject a false H0, probability of type 2 error is equal to beta. So understanding the concept. Now, let's get started. In 1990, 5.8% of job applicants who were tested for drugs failed the test at a 0.01 significance level. Tester claimed that the failure rate is now lower if a simple random sample of 15 to 20 current job applicants result in 58 failures. Does the result suggest that fewer job applicants now use drugs? Remember, we are doing application problem, word problem, and it's extremely important to write the given. It's very important to write the given. Okay. So having said that, what is it that we are dealing with? We are dealing with a binomial distribution because there are two outcomes. Either they fail or they don't. What is the probability that they will fail? 5.8%, 0.058. What is the significance level? This is alpha. What is this? N, we have a sample of 15 to 1. And how many fail? 58. That is X. So that's given. So we need to understand a couple of things. Number one, if P is 0.058, Q is 1 minus that. We calculate that. Also, this is a binomial distribution. We are going to use normal distribution to do the process. So it's an approximation. We always go to Z. And to go to Z, we have to calculate NP and NQ, and they must be large. How large? Larger than or equal to 10. In some text, 5 is fine. So I leave it for you to see that if you multiply this one by P and by Q, both of them are way larger than number 10. The next thing we need to calculate before we do the work, let's calculate P hat. P hat is X over N. 58 over 1520. And if you go with decimals, many decimals, I suggest you go with fractions. Now, the test of hypothesis, everybody. I'm going to go with 4 steps. Always do that, and then you can answer the questions accordingly. Step 1, write H0 and H1 or HA, and also write claims or and tails. And the tails always will be sitting next to H1 claim, maybe part of H0 or H1. We'll see it as we go through that. Test statistic, short TS, we calculate. For example, for this one is Z equals P hat minus P over squared of PQ over. We'll go over that. Critical value, using alpha, we get to critical value. And step 4, we make a decision. Decision has 3 parts. Part A, reject or not reject H0, or fail to reject. Then answer whether the claim is true or false by looking at the very first step. And then restate the decision. There is or there is not sufficient evidence to support the claim. So this question is asking for all of those. So rather than just going over that, I'm going to go over the process and then I'm going to answer the rest of it. That's the idea. And so again, reminding you, the test statistic for this is Z equals P hat minus P over squared of PQ over N. Bear in mind, you have access to the formula sheet table and so on, so yeah, I don't have to worry about it. So first, we're going to rewrite the information from the previous page, and now we're going to go through this calculation. So first and foremost, state the null and alternative hypothesis. H0, P is 0.058. Please bear in mind that when it comes to writing H0 and H1, you never ever use the sample statistic. You always use the population parameter. Now, as we read the question, it says fewer. So we want to check if it's less than. So H1 is the same thing, P, but less than 0.058, which makes it a left tail test, and it happened to be the claim. So when we write this, we write where the claim goes. The claim, in some instances, sticks with H0. Okay. So test the claim that the failure rate is now lower. So claim goes next to H1, and less than means left tail test. We are going to use this formula to get to the second step test statistic, calculated P hat minus P over squared of PQ over N. That's why the given gives us everything, including the P hat that was calculated in the previous page. And we write it with a bunch of decimals. Critical value, alpha is given as 0.01. This is a left tail test. You do the drawing. So the entire alpha is on the left side, 0.01. So you can use technology or the table. So this is the critical value. This area is alpha or 0.01. This area is alpha or 0.01. So from technology or the table, we get negative 2.33 roughly, or negative 2.325. Now you want to make a decision, and it has 3 parts. The first thing is what happens to H0. We go back to the very first step and we look, we make a decision. To do so, where is test statistic? Well, put it in. Negative 3.309, it's somewhere here, way into the rejection region. So this is where it ends. So the location. So you compare two numbers in traditional method. So you reject H0. So this is test statistic. You reject H0 because the value of test statistic is inside the rejection region. Now, so the test of hypothesis does this. Now you are going to elaborate on that, meaning we are going to go back to this and say what's going on with the claim. If you're rejecting H0, loosely put, you accept H1, you accept the claim becomes true. And now you read and restate. There is sufficient evidence to support the claim that the failure rate among job applicants for drugs is now lower. Result suggests that fewer job applicants now use drugs. So that's how we do the work here. Now, when we go back to a question, they're asking for the p-value also. So I want to discuss the concept. The p-value depends on what you have, a right tail test, left tail test, or two tail test. What type of test? If it's a left tail test, the area to the left of test statistic, this area, p-value is area to the left of the test statistic. If it's right tail test, the area to the right of test statistic. If it's a two tail test, area to one side times two. So if your value is negative, the p-value would be twice the area to the left of the test statistic. If the test statistic is positive, then p-value twice the area to the right of test statistic. What is the decision-making criteria? As you recall, when it was in the rejection, we would reject when we compare the test statistic and a p-value, and a test statistic and a critical value. Those are numbers. Now, p-value, they compare areas. What areas? Alpha and the p-value. So therefore, this is criteria for the p-value method. P-value is less than or equal to alpha, reject the null hypothesis. Because if p-value is less than or equal to alpha, it means it's in the test statistic is inside the rejection region. On the other hand, decision making for the p-value method, p-value is larger than alpha, fail to reject the null hypothesis. Very straightforward. So we're going to continue with the same question, and we have done the calculation. Remember, it was a left-hand test. The Z for test statistic was negative 3.309. So the p-value would be let's just draw this, the area to the left of the test statistic, meaning this area. So you're comparing this area to alpha. And this area was the alpha, right? This was the critical value, and alpha is 0.01, which was negative 2.32. So from the table, we have to read the area to the left of negative 3.309. P-value is probability of Z less than negative 3.309. You can use technology or table. You end up with 0.0005, which is way less than alpha of 0.01. And because less than or equal to alpha of 0.01, we end up with the same decision. Reject the null hypothesis. If we use technology, it's one proportion Z test. And we put the px in, and we have to make a sign is less than, gives us this. And notice, this is the test statistic that has been calculated. This is the p-value, and I'm going to write the p-value. I want to make sure everybody understands what's going on here. The p-value is 4.6727, let's say, times e minus 4. That means 10 to the power of -4. This moves this way by 4 decimals. That's how you come up with the answer, okay? And I hope you see that it's close to 0.0005. And this was also calculated. P hat 0.03816. So I'm going to erase my work. What is type 1 error? What is the probability of making type 1 error? Let's remind everybody. Type 1 error by definition means rejecting
Hija de la realidad eres.
rejecting H0 when H0 is true. Type 1 error rejecting the claim that the failure rate of job applicants who were tested for drugs is 5.8%, when the percentage is actually 5.8%. Probability of type 1 error equals alpha equals 0.01. So this is how you define type 1 error for this problem. Again, just to understand. By definition, type 1 error means rejecting H0 when it's true. So rejecting the claim that the failure rate of job applicants who were tested for drugs is 5.8%, when the percentage is actually 5.8%. Okay, so if we do that, okay. Here's the next example, a sample of 54 bears has a mean weight of 182.9 pounds. Let's assume that the standard deviation of weights of all such bears is known to be 121.8 pounds. At alpha of 0.1, is there enough evidence to support the claim that the population mean of all such bear weights is less than 200 pounds? Again, application problem, word problem. Let's write the given. Sample size, n equals 54. For those 54 bears, the mean weight is this. This is X bar, 182.9. But standard deviation, let's assume for all is 121.8. This is sigma. Alpha, 0.01. And when you see that, that means mu is 200. So you start with H0, mu equals 200. And what about here? Well, is there enough evidence to support the claim that the population mean of all such bear weights is less than? So H1 mu is less than 200, and that is the claim, and that is a left tail test. Test statistic, X bar minus mu over sigma over square root of it. That's again from the formula sheet. Let's plug in, evaluate the test statistic, becomes negative 1.0317. Critical value comes from the choice of alpha, 0.1. So we do the drawing. So this area is 0.1. We want this Z from the table or technology. We come up with the answer. And we get negative 1.285. Now, to make a decision, we're going to compare these two. So we have negative 1.285 here. Negative 1.0317 is somewhere here. Doesn't have to be to scale. And it puts us way into the non-rejection region. So we are ready for the decision. Fail to reject the null hypothesis. Fail to reject the null hypothesis because the value of test statistic is inside the non-rejection region. So let's go back. Where is the claim? If you're not rejecting H0, you're rejecting H1. Claim is next to H1, becomes false. Claim is false. Now let's rewrite it or restate it. There is not sufficient evidence to support the claim that the population mean of all bear weights is less than 200 pounds. Now, bear in mind, if we want to go with the p-value, the area, because this is left tail test, the area to the left of test statistic is the p-value. So if we go with technology, for example, we put mean z-test, and we need to put the mu sigma x bar in, and this one is less than. And here's the result. Let's look at a couple of things. One of them is this calculation is done for us, the test statistic. By the way, they don't give you the critical value normally. In some technology, for example, Excel, they do. And what is this? This is the p-value. P-value is 0.151. Is it less than or larger than 0.1? Larger than 0.1. Therefore, same decision, failed to reject the null hypothesis. Sixteen new books in the college bookstore had prices with a mean of 70.41 and a standard deviation of 19.7. Is a 0.05 significance level to test a claim that the mean price of a textbook at this college is less than $75, assume normal population. Bear in mind, when we are dealing with mu, most of the time, sigma is really missing, as it is the case here, whereas in the previous example, we assumed the weight for all pairs were given. So in this case, what is given? 16, that's n, and the price is 70.41 on the average for those 16, that's x bar, with a standard deviation s 19.7, because these two numbers pertain to 16. Alpha is 0.05. It says we want to test that it's less than 75, so that makes it mu. And so here's the test statistic, x bar minus mu over s over square root of n. So having said that, the first step is to write h0 mu equals 75. The next one, mu is less than 75, which makes it left tail test. And that is the claim. We are testing that claim. By the way, when we don't know which one is the claim, you can pick any one to be the claim and then work on that. It doesn't matter. Now, test statistic uses this formula. We're going to put in. That's why the given really is important. You do the math, you end up with that. Now, if we want to go with the traditional method, we're going to find the critical value, which comes from choice of alpha, which is 0.05. And in this case, we have to use the t distribution. Degrees of freedom is n minus 1, which makes it 16 minus 1 equals 50. Using a table, look, you put, so this is 15, 0.05, area in one take is 0.05, 1.753. Because it's left tail test, you should make sure that this is negative, so negative 1.753. To make a decision, we do the drawing. Alpha is 0.1, critical value is negative 1.753, and the test statistic is negative 0.9320, way into the non-rejection region. So fail to reject H0. Fail to reject the null hypothesis because the value of test statistic is inside the non-rejection region. Therefore, the claim becomes false. Why is that? Because if you're not rejecting H0, in essence, you're rejecting H1. And you restate, there is not sufficient evidence to support the claim that the mean price of a textbook at this college is less than $75. Now, According to the p-value, the p-value would be area to the left of test statistic, and you can look that up, or technology. So if you go with mean t-test, we put the mu x bar s, n is 16 less than, when we do the math, here's what it gives us. Number one, take a look at test statistic that is calculated. Number two, what is that? This is the p-value 0.183, way larger than alpha of 0.05, area to the left of test statistic. And that gives you the same decision, fail to reject the null hypothesis. Test in others past statistic classes have scores with a standard deviation equal to 14.1. One of his current classes now has 27 test scores with a standard deviation of 9.3. Use a 0.01 significance level to test the claim that this current class has less variation than past classes. That's one topic we're going to go over. Then there's a question that really has got nothing to do with that. Does a lower standard deviation suggest that the current class is doing better? Assume the population is normal. So we're dealing with a normal distribution. So what is given? This is sigma. In the past, it has shown that. But for the 27, n equals 27, standard deviation is 9.3. That's S. And of course, alpha 0.0. So write the given symbolic. So we are dealing with standard deviation or variation, but we compare it to a number. So step one, H0 sigma equals 14.1. Again, always use a population parameter. So having said that, what is H1? We are testing the claim that this current class has less variation. Sigma is less than 14.1. Claim left tail test. Now the test statistic for this one is chi-squared equals n minus 1 s times s squared over sigma squared. Plug in. We get the answer. Now, to get to the critical value, we are going to use a chi-square distribution here. And chi-square distribution is always positive, goes from 0 to infinity. And you need degrees of freedom. Degrees of freedom is n minus 1, so that's easy, 26. 27 minus 1 is 26. We need alpha. Alpha is 0.01. And we need the area to the right. Now, this is left tail test. So take a look. We need the area to the left. Okay. Area to the left. We need the area to the right. The area to the left is 0.01. The area to the right is 1 minus that, 0.99. So we are looking for 0.99. And the answer is 12.19. That if you go with the table. Let's do the drawing. As we can see, here's the chi-squared 11.311 is the test statistic. Here's chi-squared 12.198 is the critical value. As you can see, the test statistic is way into the rejection region. So reject the null hypothesis. Reject the null hypothesis because the value of test statistic is inside the region, the rejection region. So now we go back here. If we are rejecting H0, that means we are accepting H1, the claim becomes true. And then we restate. There's sufficient evidence to support the claim that this current class has less variation than past classes. Now, we can find the p-value using technology, okay? And the p-value would be this area. Area to the left of test statistic. By the way, a lower standard deviation doesn't suggest that the current class is doing better. It just means that the grade is more homogeneous, closer to the mean. Mean value might be different. If the mean is larger or smaller, that is the indicative of that. Having said that, we go with the chi-square TI calculator, second variable is chi-square CDF, and we put 3 entries. So we put lower is 0, upper is 11, 0.311, the test statistic. Degrees of freedom is 27 minus 1 or 26. Gives us this, and that is the p-value, which is less than alpha of 0.0. This is the p-value, 0.005. And then over here, if we stop, we change it to 6 because next to it is 6. Clearly less than alpha of 0.01, same decision. Reject the null hypothesis. Consider a population of frogs living on an island. We believe that the frogs may be members of a species called Ranopipians. The mean length of Ranopipians is known to be 11 centimeters. That's a known fact. The following length values, 10.6, 11.2 in centimeters, and so forth, were obtained for a sample of individuals from the island. Do these frogs have sizes that are consistent with them being Ranopipians or not? Are these frogs Ranopipians or not? Use a 0.05 significance level. Right away, alpha is given here. All right, so what do we need to do? First, let's write the given. Mu is 11 centimeters. Alpha is 0.05, and we count 1, 2, 3, 4, 5, 6, and n is 20. Now, we know the formulas for the mean and standard deviation. X bar is summation of x over n, add them up, divide by 20. Standard deviation is the sample. So square root of x minus x bar quantity squared over n minus 1. But you don't have to do it by hand. You use technology, whatever technology, and you get these two values, x bar. So put it into technology and get those two values, x bar and s. Now, we're going to do the test of hypothesis. H0 mu is equal to 11, and that's a claim. We are claiming, or we are hoping, that those are the type of frogs we are looking for, Ranopipians. And this one, as long as it's different, it's not. So H1 mu is not equal to 11, which makes it a two-tailed test. All right, second step, test statistic using this formula and the given, plug in, calculate, you get negative 2.3491. Traditional method, we're going to find the critical value with the choice of alpha being 0.05. Degrees of freedom is n minus 1, which makes it 19. Now, table or technology results in plus minus 2.093. So here's the drawing. This is negative 2.093. This is positive 2.093. And the critical value, negative 2.3491, is somewhere here, way into the rejection region on the left side, which means reject the null hypothesis. That's your decision. Now let's go back. If we are rejecting the null hypothesis and claim is sitting next to it, we are rejecting the claim as well. The claim becomes false. And we restate there is not sufficient evidence to support the claim that these frogs have sizes that are consistent with them being Ranopipians or Ranopipians. Therefore, the conclusion is that no, they are not run a PPS. Now, as far as technology is concerned, for example, if you run the t-test, okay, one mean sigma unknown using Excel, this is the result. Let's see what it gives us. This is S. This is X bar. So it has given us those values. Test statistic, of course, with a lot more decimal. Okay. If you start up at 0, you change it to 1. Critical value. And what is this? The p-value. And the p-value of 0.02979 is less than alpha of 0.05. We have the same decision. Reject the null hypothesis.